In this video, we are going to talk about rates of change, which is just considering how one value changes corresponding to another value. So we're going to look at this by way of example to start with two different examples of this situation. So first, we're going to consider the following. So if a curve C has equation y equals f of x, we want to find the slope of the curve at a point A. Now, to see what we mean by this, let's look at a graph. And so if we have some function y equals f of x here, what we're saying is we're going to pick some point here, which is going to be the point a comma f of a. And what we want to do is we want to find the rate of change of the point of the graph at that point. So we're looking to figure out kind of like what is the slope of this line right here. This line that touches the graph at that point and goes off in the same direction. Now we have a name for such a line. So a line that touches the graph of f of x at a point A, and then goes off in the same direction, is called a tangent line. And so what we're looking for, in a sense, is we're looking for tangent lines. We're looking for this line that touches the graph there and then goes off in the same direction. Now, the way we're going to do this is using our tool of limits. So what we're going to do is we're going to pick some other point here, say x comma f of x, and we're going to just pick another point, and now with 2 points, we can draw the line between them. And so we can find this line, and then we're just going to take the limit as this point x approaches the point A. So x is down here. We're just going to take the limit as we make this value of x go towards our value of A. And that's going to be our idea. And as we do this, the lines that we get will get closer and closer to our tangent line. And so this is our idea of what we're doing. And so slope-wise, we can figure out the slope with 2 lines. So just as a reminder, given 2 points, a comma f of a and x comma f of x, the slope of the line between them is m equals f of x minus f of a divided by x minus a. And so this is just the definition of the slope. And now we said we're going to take the limit as x approaches a. And so in this situation, what we're doing is the following. And we're going to define the tangent line formally this way. So the tangent line to a curve y equals f of x at a point a comma f of a is the line passing through a comma f of a with slope m equals the limit as x goes to a of f of x minus f of a divided by x minus a. So now this is exactly the situation we were just describing in our picture up here, that we're picking a point x, and then we're just taking the limit as the point we're picking gets closer and closer to our point A. And as we do that, we get closer and closer to this tangent line that we are looking for. Now, just a bit of notation. We call the lines between a comma f of a and x comma f of x secant lines. So these are just lines that pass through 2 points, and so this notation, this definition isn't extremely important, but you'll sometimes hear it, so it is useful to talk about. And so all we mean by a secant line is if we have these 2 points and we draw the line going between them, this is an example of a secant line. And if we picked another point, the line going between those is also a secant line. And so you're just picking 2 points and drawing the line between them. That's a secant line. And so you'll hear of secant lines at times. And then the tangent line is the limit of the secant lines as the points get close together. So let's do an example of actually finding the tangent line. And so what we want to do is we want to find the equation of the tangent line to the parabola y equals x squared at the point 1, 1. Okay, so graphically what we're doing here is we've got this parabola y equals x squared, and we've got our point 1, 1. And what we want to do is we're trying to find the line that we have drawn dotted right here. We're just trying to find the equation of that line. And so we know a point on the line already. We know we have the point 1, 1. Now we want to find the slope. Well, the slope we just said is going to be the limit as x goes to 1 of f of x minus f of 1 divided by x minus 1. Well, again, y equals x squared, or f of x equals x squared. And so that's the limit we want to compute. So we have m equals the limit. As x goes to 1, plugging things in, f of x is x squared minus f of 1 is just 1 divided by x minus 1. So we're just computing this limit, which this is the limit as x goes to 1. If we factor the top, we get x minus 1 times x plus 1 divided by x minus 1. The x minus 1s can cancel. And so we have the limit as x goes to 1 of x plus 1, which equals 2. And so the slope of our tangent line is 2. And so now we have the slope of our tangent line, and we also know a point on the tangent line. And so we're going to use what is called the point-slope form of a line to get our tangent line. And so just as a reminder, what the point-slope form of a line is. So we have the point-slope form of a line, and it is as follows. The equation of the line passing through point x1, y1 with slope m is y minus y1 equals m times x minus x1. And so this is the point-slope form of a line. Within calculus, this is typically how we will find tangent lines, is we'll typically know the point and we'll know the slope from what we just computed. And so we know those things, so we can find the line's equation using them. And so in our specific example, we have y minus 1, because the point, remember, is 1, 1, and the slope is 2. So we have y minus 1 equals 2 times x minus 1. So that is our point-slope form of the line. We normally like to write lines, though, in what's called slope-intercept form, which is just y equals something else. So we're going to rewrite this. Y minus 1 equals 2x minus 2. We're going to add 1 to both sides, and so we get y equals 2x minus 1. And so our tangent line to the parabola y equals x squared at the point 1, 1 is the line 2x minus 1. Now, the slope of the tangent line is sometimes called the slope of the curve at that point, which is what we talked about before. And the reason for that is if you zoom in on the curve around point P, it will become indistinguishable from the tangent line. At that point. So if you just zoom in on the graph really close, the tangent line and the curve itself will essentially look exactly the same at that point. And so that's why this is sometimes called the slope of the line. Not the slope of the line, the slope of the curve. So next, what we want to do is we're going to come up with a second expression for the tangent line. So we're going to just think about our situation slightly different in the picture. And so now, we once again have this curve. We're going to change where our point is. So now our point A is going to be right here. And now we're still going to pick another point. So we're going to pick some other point here. But rather than calling this the point X, what we're going to do is we're going to consider this distance between the points. So we're going to let this distance be h, and so this would be the point A plus h. And now instead of letting our point, we're still letting this point approach A, but we're thinking of that by letting h go to 0. So we're going to let the distance h between the points go to 0. And so if we write this down as a formula, if we look at the slope of the tangent line, this would be f of a plus h minus f of a divided by a plus h minus a, which is just f of a plus h minus f of a divided by h. And so our alternative definition for the slope, alternative form for slope, so the limit as h goes to 0, f of a plus h minus f of a divided by h. Now you might wonder, why do we want this alternative form? It turns out this limit's sometimes easy to calculate. So sometimes it's easier to rewrite the limit this way rather than writing it the way we had it before, which was the limit as x goes to a of f of x minus f of a divided by x minus a. Sometimes one of them's easier than the other, so that's why we wanted two different ways of doing the same thing. So let's look at an example now of finding the tangent line using this other formula. And so we want to do the following. So we want to find the equation of the tangent line to the curve y equals 3 divided by x at the point 3, 1. And so in this case, our f of x is going to be 3 divided by x. And so now we want to find the slope to start with. So our slope m is the limit as h goes to 0, because we're going to use our second formula, of f of 3 plus h minus f of 3 divided by h. So plugging things in, this is the limit as h goes to 0. Now we're plugging 3 plus h into the formula 3 over x, so we're going to have 3 over 3 plus h minus f of 3. Well, f of 3 is just 3 divided by 3, all divided by h. So this is the limit as h goes to 0 of 3 over 3 plus h minus 1 divided by h. Now getting a common denominator, this is on the top, this is the limit as h goes to 0 of 3 minus 3 plus h divided by 3 plus h, all divided by h. Now we've seen a limit like this before, where we have like this fraction over a fraction, and this becomes just 3 minus 3 plus h, and then h times 3 plus h on the bottom. So this is something we talked about in a previous video, how you get this simplification. It's just the fact that dividing by h is the same as multiplying by 1 over h. So this is the limit as h goes to 0 of negative h divided by h times 3 plus h. Our h's on the top and the bottom can cancel, and so we have the limit as h goes to 0 of negative 1 over 3 plus h. And plugging 0 in for h, we get minus 1/3. So the slope of our tangent line is minus 1/3. And so now we're going to use the point slope form of a line. So our point, remember, is the point 3, 0. And so plugging 3, 1, sorry. So plugging that in, we have y minus 1 equals minus 1/3 times x minus 3. So y minus 1 equals minus 1/3 x plus 1. Adding 1 over, you get y equals minus 1/3 x plus 2. So y equals minus 1/3 x plus 2 is then our equation for the tangent line to the curve y equals 3 over x at the point 3, 1. And so now we want to consider another situation. And so this is how we deal with finding lines, but we want to look at rates of change in another situation. And so suppose we have the following situation. Suppose an object moves along a straight line according to an equation of motion s equals f of t, where s is the displacement of the object from the origin at time t. Okay, so this is just kind of a fancy situation of saying we've got this object and it's moving in a straight line and its position is given by this function s equals f of t. This is sometimes called position function, so the function s equals f of t is called the position function of the object. So position functions are looked at frequently in physics. So this is a physics example. Now in terms of moving in a straight line, you could think of it as we've just like dropped a rock off a cliff and it's just falling straight down. Or you can think of it as we're rolling a ball along a line on the floor and it's just moving in a straight line. And so it's a situation like that. The way I typically think of it is you just have a car driving on a very straight road. And so our function s equals f of t is just telling us the position of this object. Now what we want to do is we want to figure out the speed, or what's called the velocity, of the object. Now the only difference between speed and velocity is velocity has a direction. So velocity allows us to be going backwards rather than just forwards. Speed always is assume you're moving forwards. But velocity has a direction to it. And so we're really going to be looking for the velocity. And so what we want to do is the following. So in the time interval, from time t equals a to t equals a plus h, the change in position is going to be f of a plus h minus f of a. So kind of a way of picturing that is if you think of a straight line that we're moving along, we have some position 0 down here. Then at time a, we're right here, and then h seconds later, or h time later, it doesn't have to be seconds, we're over here, and we're just computing this distance. So our change in position is just literally this f of a plus h minus f of a. And so if you think of it as a car driving, say at time 2 seconds, so this could be 2 seconds, we're at this position, and then maybe 5 seconds later, or 3 seconds later, at time 5 seconds, we're in this position. So we've just gone further along our road, and we're just figuring out how far did we move in those 3 seconds. And so our average velocity is going to take into account how fast were we moving on average. So how fast were we moving on average is going to be given by, it's called the average velocity again. It's going to be given by how far we moved, which we moved distance f of a plus h minus f of a, divided by how much time passed. And the amount of time passed, which we said was h seconds. That's what h represents. It's how much time has passed. This formula might look very similar, as this was the formula, the second formula we found for the slope of a secant line. And so now, just like what we did before, we now want to consider what happens kind of instantaneously. And so we define the instantaneous velocity as follows. The instantaneous velocity of an object with position function f of t at time t equals a is given by v of a, which is just the limit, as h goes to 0, of f of a plus h minus f of a divided by h. And so this is what's called the instantaneous velocity. And now this is just how fast is something moving at a specific point in time. So you can think of it as if you're driving in a car, if you looked down at your speedometer right at that second, the number on that the speedometer shows is going to be your instantaneous velocity. Well, this average velocity is over some period of time, how fast were you going. Now, cars change how fast they're going if you press on the brake or on the pedal. And so, because of that, you might not be going the exact same speed during this entire interval of h seconds. The instantaneous velocity is at that fixed point in time, how fast are you going? And so now, we want to do an example of finding this. And so we have a ball rolls across the floor with a position function f of t equals t squared plus 5t plus 25, given in centimeters. We want to find the velocity of the ball at t equals 3. I didn't say the units for t, but we're going to assume the units are seconds. So we're going to assume our units are seconds. And so what we want to do is we want to compute this instantaneous velocity, which is just the limit as h goes to 0 of f of 3 plus h minus f of 3 divided by h. So we're going to plug things in. So this is the limit as h goes to 0. We have 3 plus h squared plus 5 times 3 plus h plus 25. That is all f of 3 plus h, just plugging 3 plus h into our formula right here. Now we're going to subtract off f of 3, which is going to be 9 squared plus 5 times 3 plus 25. And so this is f of 3. Then we're dividing that whole thing by h. So multiplying this out, we have the limit as h goes to 0 of 9 plus 6h plus h squared plus 15 plus 5h plus 25 minus 9 minus 15 minus 25, all divided by h. So all I've done here is I distributed this negative through to, I wrote 9 squared there. That is 9. This is 3 squared, sorry. So that is 3 squared, not 9 squared, which it becomes 9. So all I'm doing is I'm just distributing this negative through here, and then multiplying this expression here out. And now simplifying all of this, this simplifies a lot. We get the limit as h goes to 0. On the top, we're going to have h squared plus 11h left. Then we're dividing that by h. So this is then the limit as h goes to 0. Factoring h out, we have h times h plus 11 divided by h. We can cancel our h's out. And so we have the limit as h goes to 0 of 11, h plus 11, which is 11. So what this tells us is the velocity of the ball at time t equals 3 is 11 centimeters per second. And so if you had like a speedometer attached to the ball or something, at exactly time 3 seconds after you started rolling it, it will be moving 11 centimeters per second. That's what the speedometer on the ball would say. And so next, what we want to do is we're going to generalize this idea. And so we've seen the same situation kind of come up twice, the same limit show up. And so we're going to generalize it to what we call a rate of change, which is the title of this video. And so suppose y is any quantity that depends on another quantity x. So y is some function of x. Y equals f of x. If x changes from x1 to x2, then the change in x is denoted delta x, which is just x2 minus x1, and corresponding to this change in x is a change in y. Namely what we will call delta y, which is f of x2 minus f of x1. Okay, and so this is kind of a bit of technical jargon that we're writing down here. What we're saying here is we have one quantity, y, that depends on another quantity x. So for instance, the position of an object depends on the time. And so that would be one relationship here, or the cost of a good being produced depends on how many of those goods is being produced. Things like that is the situation that we're in. And then we have the following definition using this. And so we define the difference quotient to be delta y divided by delta x, which is f of x sub 2 minus f of x sub 1 divided by x2 minus x1. This is the average rate of change of y with respect to x. So this is saying on average how much is y changing with respect to x, and then it actually depends on the interval, so over the interval x1 to x2. It does depend on the interval, as the average rate of change may vary. Just as a car's speed can vary over time, the average rate of change would vary depending on which interval you were looking at. Now, just as we did with velocity, when we're looking at the average rate of change, we're going to look at smaller and smaller intervals to get what we call the instantaneous rate of change. And so the instantaneous rate of change of a quantity y with respect to x, changing with respect to x, is defined to be the limit as delta x goes to 0, so as we shrink how much we're changing x to essentially 0, of our difference quotient, which is delta y over delta x. And this is just the limit as x2 goes to x1 of f of x2 minus f of x1 divided by x2 minus x1. Now we're writing it a little bit different than the way we were writing it before. This is just how we were finding the slope before, which that is also the same idea as how we were finding tangent lines, the way we were finding tangent lines, but it's also how we were finding velocities. So we've seen this same limit come up repeatedly. And in general, all it is this is just representing how fast you're changing at that specific instance in time. And so to give kind of a word example of this situation, so we've seen already slopes of lines as well as velocities, but we're going to look at an economics example. And so suppose we have the following: a manufacturer produces bolts of a fabric with a fixed width. The cost of producing X yards of fabric is C equals f of x dollars. Okay, and so we just have a function, C, which equals f of x, that tells us how much it costs to produce X yards of fabric. And so then, if we were to look at this difference quotient of delta x divided by delta c divided by delta x, this is the average change in cost. And then the limit that we had before, the limit as x goes to 0 of delta c over delta x, is the instantaneous change in cost of producing the bolt of fabric. So if we looked at a specific point in time, say at 5 yards of fabric, then this limit would be telling us the exact rate of change of our cost when we're producing 5 bolts of fabric. 5 yards of fabric, I mean. And so this is just another place where this shows up, just to give you an idea of kind of what's happening here. So now we've seen this same limit come up over and over again. And so in mathematics, when we have something that comes up over and over again, we give it a name. And so we're going to name this limit that we've been finding. And so we define the derivative of a function f at a number a, which will denote f prime of a, to be f prime of a equals the limit as h goes to 0 of f of a plus h minus f of a divided by h, or f prime of a equals the limit as x goes to a of f of x minus f of a divided by x minus a. So we have these two different definitions. Both of them are equally valid, and so you can use either of these definitions for the derivative of a function at a number a. Now, just to make this clear with how it connects to what we were doing before, the derivative, so I'll just write it down this way, the value f prime of a, which again is the derivative at the number a, is the instantaneous rate of change of y equals f of x at the point x equals a. And so this derivative is literally just the instantaneous rate of change. That is all it is. So let's look at one more example of computing, now writing it in derivative notation. So we want to find the derivative of f of x equals 2x squared plus 3x minus 1 at x equals 1. So we want to compute this derivative, and so we want to find f prime of 1, which is just the limit as h goes to 0 of f of 1 plus h minus f of 1 divided by h, which is the limit as h goes to 0. We want to plug stuff in, so we have 2 times 1 plus h squared plus 3 times 1 plus h minus 1. Then minus, so this whole piece here, this is literally what we get if we look at f of 1 plus h. Now, if you just plug the number 1 in, you get 4. So we're going to subtract off 4. Then we're dividing that all by h. So now we're going to multiply this expression out. So we have the limit as h goes to 0. And this will be 2 plus 4h plus 2h squared plus 3h minus 1 minus 4. All divided by h. So that's just from multiplying out that expression of f of 1 plus h. This is now the limit as h goes to 0 of 7h plus 2h squared, all divided by h. The limit as h goes to 0 of pulling an h out. We have h times 7 plus h divided by h. We can cancel those h's off. I lost a 2. This is 7 plus 2h. So now in the limit, we have the limit as h goes to 0 of just 7 plus 2h, which is equal to 7, because h goes to 0. So we found that f prime of 1 equals 7. So the derivative of our function f of x equals 2x squared plus 3x minus 1 at the point x equals 1 is the number 7.